Okay, General Chemistry 2 class. This is Dr. Rowley. Let's see, I need to get this Zoom thing figured out. And I think there we go. All right. I'm in a different room. So, for those of you who are in my in-class part, you know how I get affected and even distracted by the room that I'm in. Okay, I have a limited time frame to record this. So I'm going to plow through. Today is Wednesday, the 10th of February, 2021. As far as announcements go, ALEKS chapter 14, the very first part of kinetics that ALEKS unit is due on Saturday night at midnight. Don't forget lab 1 is this week. So some of you have already had it. Some of you have it to come. Don't forget when you come to lab, bring all your stuff. And exam 1. So for the in-class session, we're going to have the exam on Friday the 19th. And for those of you who are online, that's Thursday the 18th at 5 p.m. We're going to do the live Zoom meeting, and I'll be setting that up soon. Something to look forward to. We have to have just a little bit of despair today. Never before have so many people with so little to say said so much to so few. Every man dies, but not every man truly lives only to die of sheer stupidity. Attitudes are contagious. Mine might kill you. One of my favorites, life doesn't always want to be grabbed by the horns. I expected times like this, but never thought they'd be so bad, so long, and so frequent. Which brings us to kinetics. So as we move into this realm of kinetics, we're talking about how fast do reactions occur. So I think this might need to be over a little bit. All right. Obviously, I'm a professional here recording videos, and I think I'm going to stand on this side. Okay, so here we have two different chemical reactions. Here we have on the left a solution of bromine, liquid bromine, the element. Bromine is one of two elements that are liquid at room temperature and pressure. You dump some sodium in, that reaction happens immediately. It's like an explosion. However, on the other hand, here we have iron that's rusting. That's a process that takes more time. Kinetics is all about how fast the reactions occur. So when we're talking about how fast reactions occur, we're talking about reaction rate. Now, reaction rate is one of the core definitions of this chapter. Reaction rate is the change in concentration of something over the change in time. Change in concentration over change in time. So for those of you who are in math and love calculus, as I do, change in concentration over change in time, when we're talking about rates, that lends itself very nicely to differentiation and integration. Okay, where am I here? Okay. I want to begin the chapter, excuse me, by talking about the fundamentals of how molecules come together and react. So let's consider the idea of two molecules in the gas phase. So we've got a molecule here and a molecule here, two reactant molecules. These molecules, if they're in the gas phase, are constantly colliding. If you remember from the ideal gas law chapter way back in Gen Chem 1, chapter 10 maybe, chapter 11, one of those chapters, we talked about, for ideal gases, the three properties of an ideal gas: random rapid motion, extremely random, very rapid motion, perfectly elastic collision, so those molecules are bouncing off of one another, and particles are tiny compared to their space. So essentially, their volumes are negligible, the volumes of the particles themselves. Now, if we're talking about gas phase molecules reacting, what happens is they have to collide in such a way that their electron clouds penetrate, and then you split off new things. That will lead to a chemical reaction. So the reaction rate is proportional to the number of collisions per second. In other words, the more collisions you have, the greater the probability that a reaction will occur. It kind of makes sense. You only have a few collisions. Let's say, for example, that 1 out of 10 collisions lead to products. Well, if you got 100 collisions, 10 products. If you've got 1 million collisions, you've got 100,000 products. So it's related to the collision. So how fast the particles are moving really makes a difference. Only effective collisions lead to products. So here's the key right here with collision theory. When molecules collide, they have to collide with sufficient force that their electron shells get penetrated. So they have to collide with sufficient energy, and they have to collide in proper orientation. So if these two molecules, if they react, let's say they have to slam into each other like this, and then they split off into new products. Well, that's the proper orientation. They have to collide like this. But what if they don't have sufficient force? They might come along, bump each other, and just go away, because those electron clouds say, yeah, we're kind of close, but not quite. We're kind of starting to get over that energy hump, but we're not really. If they slam into each other, now all of a sudden, that force can overcome the chemical bonds that hold those things together, and you can form new bonds. Here's an example. This is an example of atomic chlorine plus NaCl, nitrosyl chloride. So chlorine is yellow-green, not the actual color, but not too far off. Here, oxygen is represented as blue. Actually, the nitrogen is blue and the oxygen is red in these models. So what happens here is as these two collide this way, we have the collision, boom, you can just feel it, right? And then all of a sudden what happens? As these two come together, the bond forms and these two weaken. So they separate here. And so this is what happens up here. Down here in the slower diagram, well, the chlorine and the oxygen, they don't really care to react with each other. And so what happens is, boom, here you have the collision, but they just bounce off of each other. Even if they have enough force to collide, as they collide, they don't have the proper orientation. This is a potential energy diagram that illustrates a little bit of what we've been talking about here. So here's the chlorine, here's the nitrosyl chloride. These are reactants. They're over here sitting as reactants. They want to react, maybe they can react. In order to react, what happens? Remember, they have to collide with enough force and in proper orientation. When that happens, what we're doing is they have to have enough energy between those two molecules. They have to collide with enough energy that they have to get over this energy hump, this energy barrier. And then, now all of a sudden, now that we're up here, and I'm going to mention what these are. So here we have reactants. We go over this energy to the top of this energy barrier. This is called the transition state. The transition state. Theoretically, at the top of this hill, this transition state, which is kind of a temporary metastable thing, actually it's not even really metastable, it can go back down to where it started, or it can go on to products. This energy barrier is called E sub A. The energy barrier is called the activation energy. The energy it takes for those molecules to get over the hump, to go on to successfully produce products. Activation energy, E sub A. Following so far, reactants, transition state, activation energy. Okay, now, as you see, if we come down here, we have the products. Notice with the activation energy is the difference in energy between where we're starting and the top of the mountain. If we were to go in the reverse direction, let's say we started with this, and we wanted to go the back way, or we want to do this to go in reverse, the activation energy would be the energy from here to here. It would be higher. It's a higher mountain to climb in order to get to that same transition state. One last thing while we're here, this versus this. Notice the energy gap between the total energy of the reactants and the total energy of the products. This energy gap right here, that is delta H. That is enthalpy. That is the difference between the bond energies here and the bond energies here. All right. Here's a bunch of data. Got to memorize? Great, because here's what I want to point out. We're talking about N2O5, and since you're naming these things at home, you probably already got it named in your head. This is a molecular compound, 2 nonmetals. Dinitrogen pentoxide goes to nitrogen dioxide plus molecular oxygen. Note the coefficients are 2, 4, and 1. So what's happening? We start with just this. The data that you saw on the previous slide, now that you had that memorized, that table contains all of the data that are used for this plot right here. So we're starting right here with the N2O5. I don't know why that's yellow, because it probably should be purple, because this is where we're starting with. This is the N2O5 right here. Notice, so this is the concentration of molarity. If this is the concentration of molarity, we're starting with no products. The products being NO2 and O2. So, since we're starting with, just picture in your mind, this is purple. We're starting here, what happens? As the reaction starts, that concentration goes down. We start with that much product or reactant, the reaction moves from left to right, and the concentration disappears. Over time, it disappears like this. It's not a linear loss of reactant. As the products build in, our coefficients are 4 and 1. This is coming in at 4 times the rate. This is simply because it's being produced in 4 times the quantity. So this, which should theoretically be this aqua green, and this, which is probably the correct color, notice what happens is that the nitrogen dioxide, the NO2, that's building up pretty fast. It is increasing at 4 times the rate the oxygen is. So change, or the rate, rise over the run. Change in concentration over change in time. So a couple of things between any 2 points on this graph, between any 2 data points on this graph, for any of these components, we can find the rate of the reaction in terms of those. And how do we find it? Let's put here and here. What's the rate between 0 and 100 seconds of the disappearance of N2O5? Change in concentration, the difference between these two, that's the change in the height, divided by the time, this distance right here. Change in concentration over change in time, that is rate. And we can get the rate from a graphical representation of data like this. The rate of appearance of NO2, notice this is 4, and the coefficient of 4. The rise here between 300 and 400 seconds, the increase in concentration of NO2 is 2 times the change in concentration, the decrease in concentration of N2O5. It's a 4-to-2 ratio. This is increasing twice as fast as this is decreasing. The NO2 is increasing 4 times as fast as the oxygen is increasing. So, how do we do this? So reaction rates. If we look at the rate of decomposition of NO2 between 300 and 400 seconds, from the chart that is, you have 2 slides ago, you may want to pause this and back it up. After I point out a couple of things, write down these numbers from the chart. 300 seconds and 400 seconds. What's the concentration of N2O5? So what's happening now is, remember that N2O5 is disappearing. So the rate of this reaction, the rate of the change in concentration over the change in time, This is a negative number for any reactant. For any reactant, the rate is decreasing, is a negative number because that concentration is decreasing. So that's where this negative comes from. And then here are the two concentrations at these time points. This is concentration at 400 seconds. This is concentration at 300 seconds. Change in concentration over the change in time. In other words, the slope is negative for any reactant because that concentration is decreasing. So we plug in the numbers and we solve for the rate. This is the rate. Notice it's a tiny number. It's change in molarity per second. That's a long time. We could do this per hour. Then this number would be multiplied by 3,600. How are you doing so far? That's fantastic. All right, so let's take a look at reaction rates. This is the general form of how to find the rate of an overall reaction. Coefficients, 2, 4, and 1. This is disappearing. This is appearing at twice the rate of this is disappearing. This is appearing at 1/2 the concentration at which this is appearing. So we standardize all of the rates. The overall reaction rate is standardized to 1. So notice here, this is the way we do this. So the rate of oxygen, it's positive because it's appearing. It is increasing. Change in oxygen concentration over change in time. How is this does this correspond to the change in concentration or the rate of NO2 appearing? Well, this is still positive because this is appearing, but notice that it's 1/4. It's 1 over whatever the coefficient is times, excuse me. So if we get change in concentration over change in time from that table, from the graph, then fitting that into the overall rate of the reaction, 1/4 of this is the overall rate of the reaction. So in other words, all of these are equal. Notice this is negative because this is a change. This is a reactant that's decreasing. 1/2, 1/4, 1/1. And that's how we get the rate of the reaction. And that's what this slide shows. So if we have A, B, B, and E, this is the general reaction rate. Okay, for worksheet 3. Worksheet 3, if it's not posted, it will be soon. Here are the data that you should use for calculating worksheet 3. So you can pause this slide, download worksheet 3, follow through the exact process we did in the previous slides because I'm not going to go through this. The examples that we used for the N205 problem, you can apply the same process here. Okay, so here we're only focused on the rate of bromine. Okay, now, the next step where I want to move, I'm probably going to cover a little bit more on Friday because right now I've only got between 5 and 10 minutes left in this room before I get kicked out. And so I'd rather end this video before people come in and start yelling at me. All right, so let's talk about rate laws. We know what rate is. Rate is change in concentration over change in time. So let's assume that we have a reaction like this. We have A and B are two reactants, and they are going to products. I seem to have lost an arrow here. Anyway, let's imagine there's an arrow, and A and B go to products. The rate is the change in concentration of A over the change in time. Now, we're going to not get into the semantics of comparing A and B yet. So we're gonna pass on that for now. So remember this, rate, change in concentration over change in time. A rate law is this. The rate of a reaction is equal to little k. This is called the rate constant. It's how fast, it's related to how fast this reaction goes. It's proportional to A raised to some exponent times B raised to some exponent. Notice that M and N are not necessarily little a and little b. We'll talk about that later on in the chapter why that's the case. So since we have this for our rate law, I just want to point out this is what a rate law is. So whenever you have any kind of a problem that says, write the rate law for, it always starts like this. Rate equals K, little k, the rate constant, times concentrations raised to some exponent. That's all it is. But it's the same pattern for every single reaction that we'll do. Remember that little k is a rate constant. Let me make one more comment about the constant, k, little k. It will be the rate constant for this specific reaction at a given temperature. So you could run it in the room I am now, you could run it across the world. As long as this reaction is occurring at the same temperature, it doesn't matter what these concentrations are, the rate law will still hold as long as the temperature is the same. If we change the temperature, we change the value of k, little k. That's why the rate law is so powerful. As we look at the rate law itself. So here's essentially the same reaction. Oh, we have the arrow this time. Here's the rate law. Rate equals k times this to some m, b to some n. Remember that these are not necessarily the coefficients of a and b. However, m is called the order of the reaction in terms of a. N is the order of the reaction in terms of b. So let's say that, and by the way, m and n are whole numbers. M and n should be whole numbers. 0, 1, 2, 3. In fact, it's almost always 0, 1, or 2. So if n is 1, this would be first order in A. If n is 2, the reaction would be second order in B. The overall order of the reaction is the sum of m and n. So if m is 1 and if n is 2, first order in A, second order in B, third order overall. Got that? Beautiful. All right, so this is where we're going to end. We're going to walk through an example here of determining the rate law. We're going to determine the rate law for this. Okay, so let me just jump forward. Yeah, okay. We're going to do this, and this will be the last thing we talk about as we end today. All right, so here we have a reaction. And this reaction is between H2O2 and I minus. This little I means initial. This is an initial concentration. This is an initial concentration. This is the initial rate. This is the initial rate as these two reactants just start to react. So we have a rate law. Okay. So here's the rate law. I hope you can see this. I'm going to turn on the light. Okay. So we're trying to find what M and N are. So as we take a look at the data, let's look at these experiments. We have 4 sets of experimental data. All of these data fit the rate law. Because remember, if it's the reaction going to concentration, doesn't matter, it's the rate. The rate is proportional to K times this raised to M times this raised to N. M and N will not change. So let's see, as we go from, let's look at experiments 1 and 2. As we go in experiment 1, the H2O2 concentration doesn't change at all. So if we're, now what we do, however, is we look over at iodide, you can see that this doubles, this initial concentration doubles. This stays the same, this double. What is the effect of doubling this concentration? What What does that have on the rate? As we look at the rate, this doubles. What happens to between these two numbers as we go from here to here? Well, this to this is 2 times. This number is double this. This number is double this. As we double this concentration, leaving this constant, the rate doubles. What is the value of n? N will be 1. Because whatever we do to this, it has a direct correlation to what happens to the rate. Let's look at experiments 1 and 3. As we look at experiments 1 and 3, this concentration is doubled. H2O2 concentration is doubled. The I minus concentration, the iodide concentration stays the same. So this doubles, this stays the same. What's the effect on rate? Look at the numbers. As we go from experiment 1 to experiment 3, H2O2 doubles, the rate doubles again. So these two are directly related. M has a value of 1. So this exponent is 1. The order of hydrogen peroxide is 1. The order of iodide is 1. It's first order in H2O2, first order in iodide, second order overall. Now, how do we find K? Now that we know what these numbers are, for any experiment, we know rate, concentration, concentration. For every experiment, we know rate, concentration, concentration. These numbers are fixed permanently for this reaction. All we do is solve for K. So solve for K. Let's use the first one. And this is 0.10. 0.10. Solve for K. It's simply this number divided by 0.01. So this becomes 0.0115. Do we care about the units? For this, I'm going to say no. We don't really care about the units. This unit is always molarity. This unit is always molarity. The unit here is always molarity over time. Often molarity per second. So for this last problem, find the rate when this is equal to 0.3 and iodide equals to 0.4. So the rate under those conditions, now that we know K, remember that K applies to this reaction under any concentration as long as the temperature stays the same. So we're keeping the temperature the same, 0.0115 times 0.3, and that's to the first power, times 0.4. All you do is multiply out, and you have your rate. See, this is pretty easy, right? Fantastic. I am going to stop here. And we will pick this up on Friday.